Now we can get started. Thank you all for joining us today. Today we have dual features. We have two farm block fellows giving a short talk about their current and previous work. We'll be starting off with Tamara Kohler. She's a 2023 block fellow here at Stanford. Recently joined in the group of Professor Adam Golden and Patrick Hayden. She previously was a postdoc at Complutense University in Madrid, and before that, she did her PhD at University College London, focusing on quantum complexity and simulation. Today we'll be hearing from Tamara about will quantum computers give an advantage in topological data analysis, and I think the emphasis today is on will.
I think it's introduction. Thank you for coming, everyone. Today we'll be talking about topological data analysis. And it's a field where in the past there's been some excitement that maybe quantum computers might give us an exponential advantage over classical computers here. And in the last couple of years, there's been a lot of research to try and really pin down the answer to the question. We're not quite there yet, but I'm going to try and give you a roundup of what we do know and what open questions remain. And so first off, what is topological data analysis? So it's a way of analyzing data, which you might have guessed. And the idea is particularly useful from what you're looking at is noisy or very high dimensional data sets. And the idea is that rather than trying to pin down, exactly what is the structure of the data, which might be very difficult if you live in high dimensional data sets, or might just be a bit pointless if the data is really noisy, and therefore the exact structure is, very sensitive to noise. So instead of trying to, pin down exactly what the geometry of the data is, instead why don't we pull back a little bit and understand the topology of the data. And the idea is this topology of data is much more resistant to noise than the exact structure of data itself. And also you can find out really interesting structural features of the data by using techniques from topology. So in particular, the tool that we're going to be interested in this talk from TDA is what's known as persistent homology. And the idea of persistent homology is that what you're interested in studying is the whole of the data set. So forget about all the other features of the data, just map the data to some topological space and study the whole from the data set. Now, there's some data sets where the holes have a really obvious intuitive meaning, like this is what the holes are telling us. So for example, if you're looking at coverage of sensors or coverage of Wi-Fi or something in some geographical space, and the holes there really are telling you this is holes in the holes in the network coverage. That's what you're looking at when you're looking at holes. There's also other data where the holes themselves might not have an obvious meaning, but studying them still can give you information about the data. So for example, if you're studying the way different groups have responded to some particular intervention, and if it's not a straightforward intervention, it's an intervention which might cause many different effects, you end up with a very high dimensional data set. Then studying the difference in holes between different groups can tell you, that there is real consistent differences between two data sets. Anyway, just studying the data itself might not be able to tell you that because it's hard to extract the noise from the real data. Okay, so that's why we're interested in studying holes in data sets. But how do you actually do that? So in homology and PDA, the idea is to start off with some cloud points. Generally, this would be a cloud in a very high dimensional space, obviously here I'm restricting that to 2 dimensions. And this cloud represents your data points. And the first step is to go from this cloud of data points to the graph. And the way you do that is you can construct a graph by adding edges between any two data points, which is separated by some distance less than epsilon. This epsilon is up to you to define, it's not given in advance. But you pick some suitable epsilon and you add edges between any point separated by less than epsilon. You then construct what's known as the T complex of this graph. But the T complex is the complex that you get by taking this graph and adding a simplex to any T in the graph. So here, where a T is a peak is size k in any graph is a set of k vertices that are where the subgraph is a completely connected graph. So here you can see we've got lots of 2 peaks. These are just edges in the graph. But we've also got 2 3 peaks. And these 3 peaks form a triangle. So we've added these triangles into this graph, into this complex, and this gives us the T complex of the graph. Okay, so this is the complex of the graph, key complex of the graph, and this is a kind of topological, this is the space that we're going to be studying the topology of. And as I said, in homology and PDA, what we're interested in is the holes in the graph, holes in the complex. So you can see here, in this particular complex, we've got two holes. For a hole in the complex is just kind of any cycle in the complex that doesn't have the simplex. So the simplices are given by the peaks, I've noted them in blue, and the holes are any cycle that isn't in blue. So you can see in this particular picture, we've got two holes. Okay, so this is very, very simple in this example. We constructed the graph, constructed the complex, and we found out that in the end, our topological space is two holes. And as I said, these holes are data sets and topological features, which are typically much more stable as noise than the raw data itself. But, as I kind of alluded to slightly earlier, the geometry that we're given by this data does depend on the distance that we use to construct the graph. So it depends on that epsilon value that we use when we're constructing the graph. And I said before, this choice is up to you. But how do you pick this choice? There's no a priori reason why one choice is better than another. And for that reason, what we end up actually being more interested in than the specific holes themselves is what's known as consistent holes. So consistent holes are holes in the data set that persist as you change the value of this epsilon. So we can see an example of that by starting with the same points as our data set. And now we construct a graph with a different value of epsilon. Here I construct a graph with a larger value of epsilon. The graph now has far more edges, far more data points to connect. We're then going to the same step again of constructing the peak complex of the graph. So again, every time we have three vertices that are mutually connected to each other, we kind of fit in that space with a triangle. If we had, if I draw a different graph and we had 4 peaks and 5 peaks, we'd be filling it in with more high dimensional spaces. But here we'll stick with a nice 2D example. Okay, so we fill in all the 3 peaks in this graph with triangles to give us the peak complex of the graph. And now you can see this is a different space to the space we had before. And it's got different holes. So there are still 2 holes there. There's still 2 holes in this space, but they aren't the same holes we had before, because the boundary of the holes is given by different vertices. So in persistent homology, what we're really interested in are the holes that persist across different choices of length scale for constructing the graph. And the idea is this is resistant not only to noise in the data set, but it's also resistant to the choices you might make as an experimentalist when constructing the graph and analysing your data. But it's important to note we can't just compute the number of holes at different length scales and find the difference. Because as we saw kind of from the example we had before, you might get some holes disappearing at different length scales, but you can also have new holes being created. So what we're interested in is not just how many holes there are at different length scales, which holes are there and which holes fit across many length scales. Okay, so this is a whistle-stop introduction to topological data analysis, and in particular the problem of consistent homology. It's a problem that we're kind of interested in quantum computing. But why are we interested in this in quantum computing? It doesn't sound like a quantum problem at all. There's no reason really to suspect that quantum computers might be useful for this problem from the way I've introduced it so far. But it turns out that holes in peak complexes of graphs are in one-to-one correspondence with 0 eigenvalues of a sparse Commission operator, what's known as a combinatorial Laplacian. And for those of you who are familiar with quantum computing, that kind of sparse Commission operator, might be kind of pricking your ears up a bit, that maybe this is, sounds an awful lot like a sparse Hamiltonian. Maybe this is somewhere where we can bring the techniques we've used the techniques that have been developed to use quantum computers to study quantum systems, maybe they might also be useful here. Indeed, back in 2016, Lloyd et al., the authors of this paper, designed a quantum algorithm, which I'll refer to as the LGD algorithm throughout this talk. And this algorithm is able to extract certain information from the combinatorial Laplacian exponentially faster than the best known classical algorithms to extract that same information. So this, being so promising, we have an object that sounds similar to a quantum object that gives practically useful information in a field totally separate from quantum mechanics or physics. And we have an algorithm that can extract information from this object exponentially faster than the best known classical algorithms. But what information does this algorithm actually extract? So instead of this algorithm doesn't count the number of holes or the number of zero eigenvalues in the combinatorial capacitance. Instead it kind of computes the number of low-lying eigenvalues. So you can see I've got this a spectrum graph here. All the kind of eigenvalues on the green line, all those zero eigenvalues, they really correspond to holes. They're the zero eigenvalues of the combinatorial Laplacian, and they really correspond to holes in the data set we're interested in. What an LGD algorithm does is it samples all the blue eigenvalues and the green eigenvalues. So it doesn't give us an exact, an exact range to the whole number of holes, but it gives something which you might consider an approximation, and it ignores kind of the higher lying eigenvalues. Now the fact that we're looking at low lying eigenvalues rather than the zero eigenvalue is not necessarily a huge issue. The combinatorial Laplacian is kind of postulated, although not really known, but low-lying eigenvalues do give some logical information. So, for example, there's if we think about just graph Laplacians rather than the combinatorial Laplacian, it is known that low-lying eigenvalues do give you information about the graph, and it's postulated that the same is true for the combinatorial Laplacian. The bigger issue with the LGC algorithm is that it doesn't actually output the number of low-lying eigenvalues itself. It outputs the number of low-lying eigenvalues normalized by the number of syntheses in the complex. And this is an issue because the number of syntheses.
I just want to revisit a slightly earlier point. So like here they say they can resist the quantization, but for example, let's say I use shadow tomography, and like say I use shadow tomography to like estimate those eigenvalues. Like I don't have to use the quantum algorithm to compute those eigenvalues or like approximate them, but just like a simulated emission operator that contain a combinatorial relation. And then to use shadow tomography to extract it out, can we also do something like that, which can also be very powerful?
I have not thought about this myself, about actually using shadow tomography. It might be able to give you some information. I don't think we'll be able to give you as much information as you can get from this algorithm. Or it might, I guess it all depends how many times you have to run it because it's essentially a sampling algorithm. So how many times do you have to run it to get enough samples to get an accurate idea of the spread of these eigenvalues? So the issue with normalizing the low-lying number of low-lying eigenvalues by the number of syntheses is that the number of syntheses is typically very, very large. It can be exponential in the size of your problem. And obviously, if you divide by this very, very large number, then typically what you'll find is that you always start at zero, you often start at zeros, because the number of poles is so small compared to the number of syntheses. So the kind of analyzing the low-lying spectrum is not kind of a serious issue, but the fact that we have this normalization is a real problem. But even though this algorithm isn't necessarily giving us exactly what we want in terms of topological data analysis, it is exponentially faster than the best known classical algorithms. And so far, actually, just a decompensation. What I mean by that is that kind of 10, 15 years ago, there were quite a number of quantum algorithms that were postulated to run exponentially faster than they could be done on classical computers, so kind of unrelated topics. And then about 5 years ago, a brilliant PhD student came along and proved that actually these algorithms could be run on a classical computer. She dequantizes quantum algorithms. And this particular algorithm resisted that kind of dequantization attack, and has so far resisted all other dequantization attacks. But there's, always evidence showing results for a few years ago, the dequantization results. There's been kind of questions asked. Is there another dequantization attack going to come along in a few years and beat this? So there's really interest in understanding, first of all, how many edit this algorithm so we get out really useful information? And secondly, can we show that this algorithm can't be run on practical computer? Okay, so I'm going to give you a little summary of the LGC algorithm, some of the algorithms that have come afterwards, kind of modifying this initial algorithm. So the first thing, as I've kind of outlined on the previous slide, this algorithm doesn't really give us use for approximation of the number of holes. It gives us some information, but this divided by this normalization by the number of simplices really does limit the utility of this algorithm. It also doesn't compute useful approximation for the number of persistent holes. It only looks at holes in a particular length scale. So it doesn't give us this idea of how the holes change as you vary the length. But as far as we know at the moment, it does run exponentially faster than can be done on a classical computer. For a particular class of complexes, but it's a large class, we don't have to worry about that. We're having some updates to the LGC algorithm. You might be thinking, okay, this computes a normalization of the number of simplices, this computes a normalization of the number of holes. But can't we just multiply the number of holes by the normalization and get out the factor we're interested in? And yeah, we can do algorithms that essentially do that. And these algorithms do give us a useful approximation of the number of holes in the complex. They still don't compute useful approximations of the number of persistent holes, but if we're getting closer, it feels like a positive step. Unfortunately, these algorithms no longer run exponentially faster than the best known classical algorithm. And especially because this normalization factor is so large, that in order to still get a good approximation with small error, when you multiply by this very large factor, you have to run the algorithms for much, much longer. There may be some very small sets of graphs where you do get an exponential speed up, but it's not kind of general. There are also further updates to this LGC algorithm, which work in a similar way. We now do give you useful approximations to the number of persistent holes. But again, these algorithms no longer run exponentially faster than the best known classical algorithm. Particularly, you do get a polynomial speed up from best known classical algorithms. So people actually working in the real world, on large data sets, the polynomial speed up can still be significant. But I guess in complexity theory, what I'm interested in is real exponential speed up, where there's less worry about improved classical algorithms and equal data. So I said I'm a complexity theorist. So what does complexity theory tell us about this problem? So complexity theory, the idea is that we try to classify problems by the resources they use in order to solve them. So for example, the amount of time or space required to solve a particular problem. One way to understand whether the LGC algorithm can be dequantized, whether there's hope of quantum advantage in TDA, is trying to understand the complexity of different problems involved. So it's doing that deciding, not counting the number of holes, not studying the number of persistent holes in a complex, but just deciding, is there a hole or not in a key complex? It's already known to be classically hard, so this is a problem we do not expect to be able to solve in a classical computer. And obviously, if we can't say whether there is a hole or not, we definitely can't study the existence of persistent holes. Although until very recently, it wasn't this held in the regime where classical quantum algorithm performed well, but recently it was shown this hardness result also holds in that regime. And in recent work, with a collaborator from my previous postdoc, we studied the quantum complexity of this problem. And what we were able to show is that this same problem, the problem of asking, does a C complex have a hole or not, is actually quantumly hard. What that means is it's among the hardest problems that can be checked efficiently on a quantum computer. And we expect that there are some problems that quantum computers can solve that they can't, some problems that quantum computers can check efficiently but they can't solve efficiently. We think this problem lies in that class. Modulo some fairly weak assumptions that we don't expect complexity classes to kind of class all down to the same class of quantum unit. So this seems like a very negative result. We've shown that this problem, which is really the simplest version of the problem we might want to tackle, is quantumly hard. We don't expect to be able to solve this in a quantum computer. And the way we show this is by showing that it's at least as hard as the hardest problem that can be checked efficiently on a quantum computer. And this is the problem of checking whether a quantum Hamiltonian is satisfiable. So given some local Hamiltonian, does it have a zero energy eigenvalue? It's known that this problem can be checked efficient on a quantum computer and almost certainly can't be solved efficiently on a quantum computer. And so very briefly, the way to prove this is essentially constructing a graph that encodes the Hilbert space of n qubits, and then filling in holes in this graph corresponding to states that don't satisfy the Hamiltonian we're interested in. So this gives us a reduction from the problem of whether or not Hamiltonian is satisfiable, whether or not a T complex has a hole. And this allows us to show that this problem is quantumly hard. Okay, so as I said, this may seem like a really negative result. We've shown that we can't expect quantum computers to efficiently solve the kind of standard homology problem. So we can't, quantum computers can't tell us whether complexes have holes or not. So in particular, they can't give us any mathematical approximation the number of holes in a complex. But there may still be variations of this problem where quantum computers can give significant speedups. So, for example, so far throughout this talk, I've been considering the problem where we've given a graph input and we want to study the holes in the T complex of that graph. But there are many other ways to describe simple complexes. And what's been less studied is what is the complexity of understanding these spaces if we're given some different efficient input. And that's an open problem which I think is interesting and where there may still be hope for quantum speedups. And the final open question, which is maybe less relevant to TDA, but I still think interesting theoretically, is what is the complexity of the problem solved by the LGT algorithm? So it's, even though this algorithm is not necessarily practically useful for TDA, it is still potentially an example of seemingly simple algorithm where there's real quantum speedup. So I think trying to understand the concept of that problem is interesting from a theoretical point of view. So yeah, thank you for your time.
Yeah, so you had these two criteria and you said that these things, the algorithm is unable to offer speed up, or it doesn't, when it does offer exponential speed up, it doesn't solve these two problems. What does it offer? So it's exponential speed up for something, but it's not those.
Yeah, so it's exponential speed up kind of this normalized number of holes, which is something, we don't have two faculties, but it's not actually useful for TDA. I think when the algorithm first came out, we were very excited thinking this is clearly a close problem and therefore it will work. But actually when you got down into the details, it turned out that even though it sounds like what you've got is close, when you actually go through it's just a bit too far away for actually useful applications.
Really fun stimulating talk. So I have a very basic question, I think, which is, can you provide an example of like a type of data where learning something about the topology, just to have some context of what
Yeah. So I guess one thing is if you're looking for like what's coverage of Wi-Fi signals, and you can if you're looking for holes in that data, it literally tells you the places where which aren't covered by this signal. So the holes themselves really give you explicit information about places that are lacking in coverage.
So we're mostly talking about physical topology mapping onto data topology.
I guess that's one of the other ones that people often talk about is like structure in the universe, where again it really is physical topology mapping onto the other one is like, for example, token preferences. There are not really physical topology, but you might be looking to kind of, again, this is where holes have a differentiation.
Like a small group to send this information to.
Yeah, exactly. So maybe we don't solve this problem.
So if the algorithm gives you exponential speed up for getting this normalized handle, why doesn't that tell you about the existence?
Because for most cases, the number of holes is so small that when you do this normalization, you get up zero. So there are some holes. So even if you had like, a polynomially large number of holes, it would still output zero. So not. So there are some cases where it can. So the partnership also doesn't say for every single example of a graph you can come up with, you won't be able to get an efficient algorithm. And it's for in particular for graphs that have like double exponentially holes or no holes, their algorithm would solve the problem efficiently. But that is not a large part of grass is not necessarily an interesting one.
We have time for you to ask another question.
We do, yeah, okay.
So coming back to this question of network, like cell phone network topology, I would think it would be much more that it would be a lower density of coverage in some area than an actual whole. Is there some way to like formulate a topological invariant, even in a situation where it's just lower density coverage?
Not likely to top of my head. I guess one way is potentially by editing the way you're forming this graph to increase distance at which you're, and then you might see holes appearing at like the distance at which holes appear gives you information about lower density coverage. So they don't appear, they don't appear figurative or very large differences in the graph.
Because I do think of Palo Alto as a whole. It's not zero though.
Yeah.
Anyway.
Okay, let's thank Tamara once again. We have a quick 30-second break if you want to get coffee or something, and then. Yeah, that's. Which is. I think we'll get started with our next speaker for today. So we have Giovanni Scuri with us. Giovanni is also a Block Doctor Fellow 2023, 2023 with us. He's working in Professor Giovanni's lab, and today we'll be hearing about what some of the work that he's doing here at Stanford. Before coming to Stanford, Giovanni was a PhD student at Harvard in the group of Professor Hong Park, and he worked on optical properties of communication. So yeah, without further ado.
Thank you so much for here for the introduction. And as Mihir said, today I'm going to talk about some of the work that we've done in the past 9 or so months, trying to make nanophotonic devices with materials that have a large electro-optic tunability and cryogenic features. So, as you all know, electro-optic materials are materials where if you apply an electric field, you can change their index of refraction. Starting from this very simple property, you can envision making a number of different photonic and nanophotonic devices. So for example, you can think of making on-chip modulators where you have confined mode and waveguide split into 2 branches, and then use the electro-optic effect to change the effective index of the 2 branches independently, such that beams going through the 2 branches pick up different phases. When they're recombined, they either constructively or destructively interfere, giving you an on-chip voltage tunable switch. You can apply very similar ideas also in the context of resonators and tune in situ the resonance of, say, nanophotonic cavities that you can add to your nanophotonic circuits and make things like lasers on chip that are also tunable. And of course, you can expand this ideas also to non-confined modes, to free space modes, start thinking of using electro-optic materials also for optical elements and tunable meta surfaces, where you can use voltage control to tune things like the focal length of a meta lens, the operating frequencies of a meta surface, or the beam steering angle of your steering device. So as you can see, just from these kind of very simple examples, there are really a number of different applications that you can think of for electro-optic materials. So you can think of using your optical modulators for optical communications, or active optical elements for holographic displays, or even use active optical elements in some quantum applications. Say if you want to get a very nice fast spatial light modulator that operates at optical frequencies to control your arrays. And of course, even in the realm of quantum, which is maybe what's most of interest for this audience, electro-optics can be used for other applications as well, including what I'll get to in maybe a few slides, which is quantum transductions and connecting multiple superconducting qubit processors with one another. Really, the work that we've done in our group in the past year or so is trying to answer the question of whether we can find materials that have stronger electro-optic response than state of the art currently. And this is both to make kind of more efficient devices, but also really to open up new applications that are currently not possible with the materials we use nowadays. And we've worked with materials that operate both at room temperature and cryogenic temperatures for a number of different applications. But for today's talk, I'll mainly focus on our work that's on electro-optic materials that have large tunability at these low temperatures. And really, like, one of the big motivations for this type of work is this idea of connecting multiple superconducting qubit processors in different cryostats or different dilution refrigerators with one another. As you all know, superconducting qubits operate at these very low temperatures, so they need a dilution refrigerator to bring them down to a few or tens of millikelvin. Which means that when you're trying to scale up the number of qubits, you'll ultimately reach a limit of the cooling power of your cryostat. So then if you start thinking about how can we increase it further, you need to start thinking about also how do we connect different dilution refrigerators with one another. And this is a field that's very active even here at Stanford in trying to find how best to encode the microwave qubit information, the information from these superconducting qubits, which is in the microwave domain, try to encode that information into the optical domain so that you can overcome issues with thermal noise that will affect the performance of the superconducting qubit. And really, there are a number of different directions that you can take in this regard. There are also mechanical systems that you can use for transduction. But what I'll primarily focus on in today's talk is how can we use electro-optic materials to achieve this transduction, and why we would want to look for materials that have large electro-optic tunability, specifically at cryogenic temperatures, in order to achieve this goal. And as you can imagine, I mean, the reason we want to do everything, by the way, at cryogenic temperatures is, of course, when you do this transduction, you want to be able to do it when you don't have sources of thermal noise, so you want to do it directly at these very low temperatures. So taking a step back, how can we use electro-optics for this application? If we go back to this initial definition of electro-optic materials, where you get a change in your refractive index when you apply an electric field, this proportionality constant, which just tells you how much of a change in the refractive index you get, known as the Kohler's coefficient, is actually proportional to the nonlinearity in the material itself. So if you have an optical beam that propagates through a material that has this electro-optic tunability, and you change your refractive index n, you'll get a change in the phase of the optical beam that's being material. And if instead of having a DC change in the refractive index, you now apply a modulation frequency omega to that change in the refractive index, the beam propagating through an electro-optic material will pick up sidebands at plus or minus that modulation frequency of your electric field. So you can really see this as a three-wave mixing problem, where you have an optical photon at a frequency that's in the terahertz or hundreds of terahertz regime. You have another signal, your applied electric field, that has a specific modulation frequency omega. And depending on the strength of this type 2, again, you'll get as an output a beam or an optical signal that includes the frequency from your initial optical photon and from your modulation frequency of your electric field. And you can see right away how you can then use this three-way mixing problem to go from the microwave to the optical regime. Because if now you use, instead of a arbitrary modulation frequency of your electric field, the microwave signal that you want to transduce into the optical regime, then you can get exactly that. And so you can, for example, draw a diagram like this of a system that you might want to use in order to achieve this microwave to optical transduction. We have your microwave signal that enters a circuit that's gaining a Chi2 material. You can embed that into an optical cavity to improve the interaction with light, and then you'll get indeed transduction from this microwave. And really what's kind of a key takeaway in this case is that the efficiency at which you can achieve this conversion between these very far kind of energy scales is proportional to the strength of your Chi2, and specifically, at least in the low conductivity regime, it's proportional to the Pockels coefficient squared. So really, achieving a large Pockels coefficient will give you efficient conversion. And specifically, if we're thinking about applications in transduction, we want to achieve this large Pockels coefficient at cryogenic temperatures. So this is what we set out to do: look for materials that have large Pockels. And of course, the first step can be just to look at other leading systems that operate primarily at room temperature. And there is indeed kind of a whole wealth of different types of materials, both bulk crystal, thin films, and also thin films on silicon. And all of these operate with different efficiencies, but crucially, many of them either operate worse at cryogenic temperatures, or at best, they operate the same way, so at the same Pockels coefficient as they do at room temperatures. So can we do better than these new systems? And how do we look for new materials that might operate in a better way than what we know currently? So to look for new materials, I'll go back to these three-wave mixing pictures, and specifically also add a four-wave mixing picture, which is also relevant for a quadratic electro-optic effect instead of a linear electro-optic effect. And recalling that Miller's rules tell us that this Chi2 and Chi3 is proportional to the products of the linear susceptibilities at the relevant frequency in these three and four-wave mixing cases, we can simplify this by understanding that in this linear and quadratic electro-optic effects, or a single frequency or two of these frequencies are microwave or near BC, while the other two, of course, are in the optical domain. So we see that the strength of these Chi2 and Chi3 are going to be proportional to your dielectric constant and your dielectric constant squared for the linear and quadratic electro-optic coefficients, respectively. And so then our problem in looking for a material that will display strong electro-optic tunability becomes really a problem of looking for materials that have large dielectric constants at low temperatures. And this is actually something that you can also check at room temperature if it's the case. And indeed, you can see the materials that have the largest electro-optic Pockels effects are also the ones that have the largest dielectric constants, at least among this group. So the material system that we started investigating is ABO3 type ferroelectric perovskites. And the reason is that we believe that they will have a large dielectric constant at these low temperatures, especially when they're approaching a phase transition from a paraelectric to a ferroelectric phase. And we can understand why this is the case by drawing a very kind of qualitative energy and electrical crystal polarization diagram at three representative temperatures: above Tc, which is our phase transition from a paraelectric to a ferroelectric phase; at Tc, so at the transition temperature; and below, when the system is fully ferroelectric. So when we are above this phase transition, we see that there is this quadratic looking potential where about zero polarization where really the amount that you can change the polarization depends on the specific material properties that you're looking at. As you're approaching this phase transition, this potential becomes very flat, which means it's very easy to change the crystal polarization in the system without paying much of an energy cost. So that means it's very susceptible, right, to changing crystal, to changing this electric polarization. And then, of course, when you are below the transition temperature, the system has two favorable non-zero electrical polarizations, and about or around those non-zero polarization, you have again quadratic potential. So we can draw this intuition in this plot of the electric constant over temperature, again, kind of very qualitative, and you see that as you're going from high temperatures towards the transition temperature, you expect this dielectric constant or the susceptibility to increase. And then as you reach this phase transition temperature, you expect it to be maximal, and then it will decrease once again once you have a ferroelectric material that has these two kind of potential minima. And crucially, there's also another thing that changes, of course, as we go from this paraelectric to this ferroelectric state, and that is that your material goes from being non-polar to polar. So in this higher temperature regime, you're mainly focusing on an electro-optic effect that's quadratic. Whereas when you break the symmetry, then you can have also a linear electro-optic effect in systems. But what we did was really try to maximize epsilon, which shows up in both of these situations. And to do that, we want to look for a system that approaches this paraelectric to ferroelectric transition at close to T=0, or at these cryogenic temperatures that we're interested in. There is one such system that actually kind of fits these requirements. It's known as strontium titanate. Some of you might be familiar with this type of material. It was actually used as a fake diamond in some applications. So it has very similar properties in terms of the refractive index in the optical domain to diamond. But it's been studied also, even starting in the 70s, as a material to make very large capacitors, and specifically also what's been studied is the dielectric constant as a function of temperature, which it's been shown to have a very large dielectric constant, over 20,000 at these cryogenic temperatures. And it's believed to be due to the fact that it's actually in a quantum paraelectric phase at these low temperatures. So it never actually undergoes a transition from paraelectric to ferroelectric, but stays in this quantum paraelectric phase where you do have two non-zero polarizations that are energetically favorable, but the wall is small enough that quantum fluctuations will never bring you to one polarization or another, which means that you're essentially in this regime of being close to the phase transition temperature for a relatively large range of temperatures below 10 Kelvin, which is actually something that we like because it means that you don't get the instability in your dielectric constant that you would get if you were using a material that's very close to a phase transition. But the other second point is that it also, as a result, displays a quadratic electro-optic coefficient as opposed to a linear one, because again, we don't have this breaking symmetry in this quantum paraelectric case. So given that we thought we found a promising material, of course, our first measurements were to actually test that the material system that we were using is consistent with what we expect in terms of having a large electric constant. And we built a nice Montana cryostat setup to investigate exactly that, and started doing some measurements on both samples of strontium titanate that have fabricated gates on the top and the bottoms. And they were in this kind of field effect, in this capacitor format. And from that, we could measure, the capacitance as well as the dielectric constant as a function of temperature. And we see indeed that at the lowest temperatures that we can reach of around 5 Kelvin or so, we get dielectric constants that are on the order of 20 to 25,000, depending on the specific material that we are working on. But of course, the other important thing that we had to look at was how does this dielectric constant behave when we're applying a bias between this top gate and the bottom gate, so an electric field. And that's because we expect it to be in this quadratic electro-optic regime where you do have to apply a bias in order to see that. And so we did this measurement as well, and we looked at non-zero fields, again with a BC bias, still measuring the dielectric constant as a function of temperature. And we see that for increasing applied electric fields, we get lower and lower values of dielectric constants, but they're still quite high for these non-zero fields on the order of 5 to 15,000. And we can also probe this exactly in our full phase space, and we see what we see in these line cuts is that we get a general increase of the dielectric constant as we're going from order 100 Kelvin to 10 Kelvin, with the maximum being close to zero applied bias in our steam. So given that, of course, our next measurement was to actually look at the electro-optic response of the material, which has not been investigated at these temperatures or even at room temperature, of course. And so for that, we built a Mach-Zehnder interferometer with our cryostat, where we just have an incoming 1550 beam that we split into two arms. One arm just propagates outside of the cryostat, whereas the other arm is focused onto our bulk material, is transmitted through, and then recombined with the initial arm. And then we use a detector and a spectrum analyzer to infer the phase that this arm picks up from the STO, and from that, of course, infer the change in the index of refraction and our Pockels coefficient. And we also add basically both a DC bias voltage as well as an AC modulated voltage to read out our electro-optic coefficient. And once again, that's because we're in this quadratic electro-optic regime where you need to apply a bias field in order to define an effective Pockels coefficient in our system. So we can plot this effective Pockels coefficient as a function of the applied DC bias on our bulk material. And we see, as expected, around zero electric field, a very small Pockels coefficient due to this quadratic electro-optic effect, and then it rises very quickly to values of around 450 at non-zero bias fields. And then as we increase further, of course, we expect this effective Pockels coefficient to have a bias term that's increasing. So that brings this effective Pockels coefficient up, but the square of the dielectric constants decreasing much faster. So the signal then starts saturating at these high electric fields. But regardless, at these intermediate fields, we get very large Pockels coefficient of around 450 picometers per inverse volt, which is more than 15 times larger, or approximately 15 times larger compared to lithium niobate, and a few times larger than other systems that have also been studied. We can, of course, check the temperature dependence of our electro-optic response as well. And we see, as we expect, a sharp decrease as we're going from this quantum paraelectric to a classical paraelectric phase. And also look at our entire phase diagram of temperature and electric field, and indeed see that we're optimized at this specific non-zero electric field. And then, of course, these properties, these electro-optic properties, are also linked very closely with other properties of the material system itself. So then we started first looking at the frequency dependence of the Pockels effect, and we see that there is a decrease in our Pockels coefficient that's actually not due to any material properties itself, but can be very easily modeled by looking at what the maximum voltage between this large capacitor is as a function of frequency. So this decrease in Pockels coefficient is not due to a material property itself, but just due to how we're doing the measurement and what the configuration of the device is. So in future nanophotonic devices, we expect this to be quite different. And we also looked at the piezoelectric response, which, as I mentioned, was a response that we also thought would be linked to this quantum paraelectric phase in the material. And we see that indeed it's also quite large at these cryogenic temperatures. So this 2D plot showing temperature and electric field is very similar to our electro-optic response, except that now we're getting the largest piezoelectric coefficient in this material at not the lowest temperatures, but some intermediate temperatures. Regardless, this is still a large piezoelectric response in this low temperature regime, and actually around 10 times larger than the thing. So this was actually quite exciting for us, and we started fabricating nanophotonic devices with this type of material. But before I get to that, I want to also point out that we're trying to see if we can further improve these properties by doing some additional kind of materials research on this strontium titanate. And this is inspired by some previous work from around 20 years ago that has shown that if you actually change the isotope of oxygen that you have in your strontium titanate and go from almost a purely oxygen 16 material to around 40% oxygen 18 and 60% oxygen 16, you actually expect an even greater increase in your dielectric constant. And beyond a certain value, you also expect to be able to reach a fully ferroelectric state as well. So working with some collaborators at University of Michigan in a group of Professor Lee, we actually got a material, a first batch of materials that has around 25% oxygen 18 concentration. So not this kind of optimal 40%, but getting there. And we see that already we see more than a factor of 2 improvement in our dielectric constant. So this red curve is what I showed previously, and this blue curve is this new material that has almost 50,000 dielectric. And so we're working in parallel both on this direction, but then as I just mentioned, we're also working on creating thin film devices. And we have 2 approaches. In this case, the first is a purely monolithic platform. So thinning down this bulk material of strontium titanate to get high quality thin films, such that we can do nanofabrication directly on that high quality thin film structure and do our photonics directly there. The strontium titanate actually be the waveguides amplifying the modes. And to do that, we're using some of the techniques that were developed in our group by Daniel Rugen and others in the context of silicon carbide. So using this grind and polish technique where we have a bonding step, a mechanical grind step, followed by a CMP polishing step that then gives high quality thin films that we can use for photonics. And again, the advantage of this is that you start from bulk materials that are the highest quality materials that you can get your hands on. And so this is something that we are still progressing towards. And the second thing that we are trying is heterogeneously integrating our strontium titanate with other types of materials, specifically silicon carbide, amorphous silicon, and SOI. And so we've been working also in collaboration with the Dion group to develop an SOI process where we can bond SOI to STO, do a deep silicon etch, add an additional buffered oxide etch, and get thin films of single crystal silicon directly onto our strontium titanate. And now we're working on this last step to actually make the photonics. So with that, I'll conclude with just a summary of what I've talked about today. So I've shown you that strontium titanate has a very large electro-optic response at temperatures below 10 Kelvin. And we think this large electro-optic response is consistent with it being in this kind of quantum paraelectric phase. We're working towards making films of STO in order to actually do kind of on-chip active photonic structures and motivated this work in the context of making both active optical elements, but potentially also trying to apply some of these ideas to quantum transduction. And I want to acknowledge my group, everyone who has worked on this, specifically Chris Anderson and I have worked a lot on this project, but also Casper, Josh, Daniel Gunho, and Alex White. And recently we had a new addition as well, Sanjan. And also our collaborators in Professor Amir Safavi-Naimi's group and Professor Dan Dion with Sahib. We've done a lot of this work, and other collaborators, of course, other projects that we've been involved in. And to take any questions.
It really surprised me, but I have a question. So in general, there's this Kramer-Kronig relation. Right? It says that if the real part of the index goes up, the imaginary part also changes. I guess what I'm wondering is, if you're gonna try to make resonant devices, how close to a transition can you go before the sort of you hit some impedance match point at where you're dominated by the loss coming from being close to the transition? Are you almost there? Is there more space to win?
Yeah, so this is actually something that we are looking into. Also generally, of course, losses in the system and so on. We don't have a good answer yet, but part of it is because we're also looking at these different types of material that maybe for different type of isotope concentrations and maybe get us over the transition so that then we would have less. Yes.
Is there an issue with decay time of electro-optic response? That like, can you like smoothly tune up and tune down on the electro-optic response, or is there like an issue of like a sort of lag time? Just thinking of STO as like a ferroelectric. If there's any.
So you mean like how fast can we go from here to here, or?
Like if you want to lower your electro-optic response,
Yeah.
is there like any sort of lag time on that, or you can smoothly tune up and down?
The main lag is dependent on basically your how well you're applying bias to your system.
But there's no hysteresis.
There is no hysteresis in this ferroelectric scenario. Of course, if you get into a ferroelectric, then you would have hysteresis. Any last questions? Okay, if not, let's thank Giovanni.